All right, welcome to Mancinelli's Math Lab. I wanted to cover this idea because I touched on it yesterday. Well, I just mentioned it, but now I want to actually show that it's true. It's a little bit tricky. Let me do my best to help you remember this fact and also see why it's true. So I want to show the following. I want to show that if you have a continuous random variable x, and we're going to assume that it's defined for positive real numbers, if you have this continuous random variable with the memoryless property, so those are the assumptions, that this implies that this continuous random variable is an exponential random variable. Now I have if and only if, because if it's exponential, it's memoryless. And so I don't think I'm going to prove that side. It's very easy. It's just, there's not much to it. Just use the definition of memoryless along with the definition of what an exponential random variable is. So again, I just want to show basically that if we have a continuous random variable with a memoryless property, that it must be exponential, because that's the part that is less easy to see. And actually, this is important because we should be thinking, the importance of this result is that the exponential random variable is the only continuous random variable with the memoryless property. So there's no other ones. If it's memoryless, it's automatically exponential. Let's get into it. So, again, we're going from left to right. And if you've written a proof, you know what I mean when I say that. So we're assuming x is continuous with memoryless property. So, again, so proof. So I want to suppose that x is continuous with memoryless property. So what does that mean? That means that we're going to suppose that the probability that x is greater than s plus t is equal to, given that x is greater than s is equal to the probability that x is greater than t. So again, we're assuming the memoryless property. So suppose that it's true. Suppose that x has the memoryless property. This is what it is. And now I want to show that it must be an exponential random variable. Let's just use the definition of conditional probability. The left-hand side, by definition, this is the probability that x is greater than s plus t and x is greater than s divided by the probability that x is greater than s, and this is equal to probability x greater than t. So I haven't done anything fancy whatsoever. All I've done is I've used the definition of conditional probability on the left-hand side. This is the definition. Remember, the comma means and. Think about this for a second. If x is greater than s plus t and greater than s, how could both of those things be true simultaneously? Well, it must be greater than s plus t. So therefore, the probability that x is greater than s plus t divided by probability x greater than s equals probability that x is greater than t. So what this does for us is this sets up an interesting consequence. This says that the probability that x is greater than s plus t is equal to probability x greater than t, probability x greater than s. This is interesting, and we're going to define a function to show you what I mean a little bit more, but basically what you should be thinking here, if you've taken modern algebra classes, you've seen things like this. Addition, here I have s plus t, turns into some kind of multiplication. So that's kind of the motivation, I think, as to why we want to define a function here. Let me just mention that I did not come up with this proof, but I'm going to show you the details, basically, that others don't show. And hopefully this will be clear to you. So we're going to let g of t equal the probability x greater than t. Then what does this mean? So then what comes from this is that g of s plus t equals g of s times g of t. So hopefully you're seeing that. There's not too much really going on there. It's just a direct consequence of this, right? This is g of t. This is g of s. And this is g of s plus t. And just by the definition of how we define g, that's true. So hopefully you're seeing that. All right. Now what? Well, we want to arrive at a few results for g. So what can we say about g? Now remember that we're considering x being from 0 to infinity. Okay? What can I say about this function g? Okay? Well, we can say that what is g of 1 over n? Where n is a natural number. Okay, g of 1 over n is equal to what? Well, I'm going to do something slightly tricky. So we have g of 1 is equal to g of 1 over n plus ... 1 over n. What am I doing here? What I'm doing here is I'm adding 1 over n to itself n times. If I add 1 over n to itself n times, then that's going to be 1. So 1 over n added to itself n times is 1. So this g of 1 is g of 1 over n added to itself n times. Nothing crazy going on there. Now what does this property say I can do? This property says that addition turns into multiplication. So then this must be equal to g of 1 over n times g of 1 over n times g of 1 over n times g of 1 over n n times. If I multiply g of 1 over n to itself n times, that's g of 1 over n to the n. So what did we just show here? So then this shows that g of 1 is equal to g of 1 over n to the n, and therefore g, just take the nth root of both sides, so g of 1 over n is equal to g of 1 to the 1 over n. So this is an important result to arrive at. Now I want to say something about a more general fraction. So this was all for all n natural number. There's nothing special about the n I chose. This is just for any natural number n. We have that. What then is equal to, what can I say about just a general rational number? So what about g of m over n? What is that equal to? And this is for m in natural numbers, where their greatest common denominator is 1, so they're coprime. All I want to say is that I can't reduce m and n anymore. I mean, think of it, you don't want it to be like 2 over 4, it's just a half, right? It doesn't really matter, but for any rational number, what can I say about this quantity? We have the following. So we have that g of m over n, this is equal to g of 1 over n plus ... 1 over n. So what am I doing here? What I want to do here is I'm just adding 1 over n to itself. How many times? Well, how many times do I need to add it to itself to get m over n? M times. That's all well and good, because now I can resort back to this property up here that says that addition turns into multiplication. So therefore we get g of 1 over n to the m. But we already know, we already have something for g of 1 over n. So keep this in mind. So think about what we have. So then we have the following, that g of m over n is equal to g of 1 over n to the m. Thus, g of m over n is equal to g of 1 to the 1 over m to the m. Why is that? Because we just said a second ago that g of 1 over n is g of 1 to the 1 over n. So I've made a substitution from here to here using this. Okay. Using star from above. Okay. So now this is where things get a little bit hand-wavy, and you would need to take a real analysis course to understand this more thoroughly. But the idea now is this. Any rational number, well, the rational numbers as a set are a subset of the real numbers. Furthermore, the rational numbers are dense in the real numbers, meaning that between any real number there's a rational number. And what you can show is that the rational numbers, any real number can be thought of as the limit of a set of rational numbers, meaning that for a real number, I can choose a real number, and I can create a sequence of rational numbers that will converge to that real number. So, what we're going to say is the following. This is, again, this is where things get a little hand-wavy, but so since the rational numbers are a subset of real numbers, and that the rational numbers are dense in the real numbers, we can say the following. We can say that what? We can say that g of a is equal to g of 1 to the a for any A in R. So this is the important piece here. And I'm going to need to give myself some more room. So let me go ahead and get another piece of paper real quick, and I'll keep this above. So now, how do I want to do this? So we have that. So I just showed to you, convinced to you what we have. So since g of A equals g of 1 to the A for any A and R, what does that do for us? Well, we can certainly write this. G of A is equal to e, the exponential, raised to the a times ln of g of 1. So g of 1 is just a probability. It's a number. And furthermore, it's positive, so we can take ln of that. And so, and again, a is positive, so real numbers greater than or equal to 0. Okay, now we're going to claim that lambda, the lambda that we're used to seeing, is equal to negative ln of g1. So, in fact, we can just let lambda equal this so that we have g of A is equal to e to the negative lambda A. This looks like an exponential. This looks like an exponential random variable. Specifically, it looks like the survival function of an exponential random variable. So what you can also be sort of thinking here is that i.e. g of x is equal to e to the negative lambda x. And I'm going to say what I just said a moment ago. This looks like the survival function of an exponential random variable. And that's exactly what it is. That's exactly what it is. So remember how we defined what g is. So recall, what was g? G of t is equal to the probability that x is greater than t. So what have we just said? So in conclusion, g of t, which equals probability x is greater than t, is equal to e to the negative lambda t, where lambda is equal to negative ln g of 1. So now think about this for a second. I mean, you should hopefully be saying we are absolutely done with this. This is game over. This is it. This is it, right? I mean, let me say this another way real quick. So hence, we have that the probability x greater than or equal or greater than t is equal to e to the negative lambda t, or in other words, we have this. We have that the probability that x is less than or equal to t is equal to 1 minus e to the negative lambda t. i.e., what is probability x less than or equal to t? That is the cumulative distribution function. Cumulative, the CDF, is equal to 1 minus e to the negative lambda t. This is the CDF. Of x. Remember, I mean, beforehand we don't know what x is, but we're saying now, we've concluded basically that x is, it has to be an exponential random variable. If it has the memoryless property, it must have been exponential all along. And I mean, one more step, if you don't like this, take the derivative. I mean, let's just write it real quick. i.e., this is really shouldn't even have to say this. The PDF is lambda e to the negative lambda x, or t, or whatever. I guess to put an x here, this should be an x. But hopefully you're getting the gist of it. Conclusion. So hence, x is an exponential random variable. That's it. So I urge you to prove the other direction. In other words, assume that you have an exponential random variable x. Show that it's memoryless. It's quite easy. It's just a little bit of algebra, really. So not much going on. All right. I hope this was helpful. Hopefully you'll remember this now. Anytime you have a memoryless continuous random variable, it's automatically exponential. So it's the only one. All right. Tell me what you think. Please like.